All right, here we are with lesson 2.4. I think we're at already. Segmented motion. What is it? How do we deal with it? The good news is you already have all of the tools you need to solve this. So, segmented motion is if a constant acceleration motion changes into different constant acceleration motion, then we cannot model the motion using just one equation. Each interval of constant acceleration is called a segment. So if the constant acceleration changes into another constant acceleration, then we have to deal with two segments of motion. Hey, get out of my way. This lesson will consist of 3 example problems. Let's look at all 3 examples before we learn how to solve them so we understand what segmented motion looks like. All right, so briefly, here we go. We've got a ball dropped from rest at the top of a 420 meter tall building. The ball falls freely until it reaches a speed of 60 meters per second and then reaches terminal velocity. How long does the ball take to reach the ground? Right? So hopefully by now you can look at this and say, okay, I don't know where to start. At least say that. Maybe you can see there's a height. Then there's a velocity. So maybe you're thinking conservation of energy, I hope. But then it talks about terminal velocity, which we don't know. So there's different things going on. First, we have the ball is in free fall until it reaches a top speed of 60 meters per second. And then the ball has a constant speed until it reaches the ground. This is what terminal velocity means. It means that the air resistance is becoming enough so that the falling object can no longer speed up. On to example 2, emergency stop. A car drives at 40 meters per second when a cow crosses the road up ahead. It takes the driver 1.5 seconds to realize the hazard and move his foot from gas to brake. Then, when the brakes are fully applied, the car decelerates at a rate of 8 meters per second squared. How far does the car travel during this entire sequence? Here are the segments of motion. First, we've got the car traveling with a constant speed of 40 meters per second for 1.5 seconds. And then we have the deceleration that happens from 40 meters per second to rest at a rate of 8 meters per second squared. And then our last example problem is going to be this. A traffic light turns green and a car accelerates from rest at a rate of 2 meters per second squared until it reaches 20 meters per second. The car then travels with a constant speed until the next light turns red up ahead. Since the driver is very close to the next light, the driver brakes hard at a rate of 5 meters per second squared, coming to a rest. If the two lights are 260 meters apart, how long does it take for the car to go from rest to rest? All right, segments involved with this big long paragraph. So speaking of which, big long paragraph. This can be intimidating, right? How do you even start this? Where do you begin? What's going on? So the whole point of this lesson is to not try to do everything all at once, but instead chop up the problem into small bite-sized pieces that you can understand and you can deal with. Okay, so for example, accelerates from rest at a rate of 2 meters per second until it reaches. We have a final velocity, we have an initial velocity, we have an acceleration. From there we can find time, we can find displacement, whatever it is we're needing. And then the next one, the car travels with a constant speed until the next light turns red up ahead. So this is the whole idea, is just taking your time reading the questions, understanding what's actually happening, and then applying what you already know to small pieces of it. I don't know where my face is, so I hope I'm not in the way, but I'm guessing I probably am. Sorry about that. Here's the segments of the motion. The car accelerates at a rate of 2 meters per second squared until it reaches 20 meters per second. Car travels with a constant velocity of 20 meters per second, and then the car decelerates from 20 meters per second to 0 at a rate of 5 meters per second squared. These sorts of problems are most easily solved using a segmented motion diagram. This is a diagram for 2 segments. Note how each segment is separated by a vertical line. We have all the stuff that's happening in segment 1 here, and then our vertical line, and then segment 2 right here. This is a diagram for 3 segments. Note how each vertical line has 3 quantities above each, and each segment has 3 quantities below it. The quantities over the top of the vertical lines give information about the object's motion at the moments one segment ends and another begins. X is position. T is the clock time when one segment ends and the next begins. V is the object's velocity. Delta X is the displacement of the object during that segment. Delta T is the time interval that the segment lasted. And A is the object's acceleration during that segment. To fill in the blank in the segmented motion diagrams, we need to know to use each of the following equations. The trick is to knowing which equation to use to fill in which blank. That's what we're going to be practicing this lesson. Example 1, next video.